Hello and welcome back. Now we are going to hear the second talk in this invited session. And yeah, I hope you all prepared your homework from yesterday, because now it's my pleasure to let Manuel give his second part of his tutorial on oligomorphic clones.
Yeah, thank you very much. Thank you for being back. Yeah, so today is the second part. I want to quickly recap what we have seen last time in tutorial part number 1. So I have introduced oligomorphic clones. So it's very easy to remember. These are those clones on a countably infinite set where you have, for every fixed arity, finitely many invariant relations of that arity. And we have seen some of the fundamental results. So we have looked at pol-inf, inf-pol. All this works nicely. We have looked at congruences. Also, congruences are quite well behaved for oligomorphic clones. We have finitely many, for example. We have also seen that Birkhoff's theorem still plays an important role. And we have seen, well, that's less straightforward what's happening there. We have seen that they are not idempotent. Oligomorphic clones are never idempotent. But the thing to fix it in some situations, in some situations you can work instead with model complete course. Model complete course. And then I was running out of time. Today, I want to continue with the more advanced results that we have in this area, quite recent ones, obtained by many more. I have just listed 4 names. There are many more working in this area. And then I want to also discuss applications. And the running application that has driven the development in the area is the complexity of the constraint satisfaction problem. So this will be at the center of today's talk. But there are other applications. CSPs are not the only application. We will, and this is what I want to discuss today, we'll see applications in finite model theory and also in the theory of relational algebras. All right, so what is a constraint satisfaction problem? We have already seen in previous talks and tutorials of this conference the definition of a constraint satisfaction problem, but let me just point out that it's really not essential for the definition at all that we fix a finite structure. Exactly the same definition that you have seen for finite structures, the constraint satisfaction problem of a finite structure, it works for infinite structures as well. I fix a structure with finitely many relations. And the constraint satisfaction problem is given a primitive positive sentence. Does the sentence hold in my structure, yes or no? So a primitive positive sentence, you can imagine it as a finite set of constraints, and we would like to satisfy the constraints. And an example that plays an important role also in this talk is the constraint satisfaction problem for the K3, for the clique with 3 vertices. It's a finite structure, but it will be important also to study the complexity of infinite domain CSPs. This one is an NP-complete CSP. And we have seen in the previous talk by Jakub Oberschall that 2 examples, famous ones for finite domain CSPs, positive 1 in 3 suds, not all equal, 3 sud, for example. Also, Boolean linear equation systems can be coded as the 2-element CSPs. What is new now is we also get problems like graph acyclicity. Input, a digraph question, is there a cycle, a directed cycle, yes or no? And can be solved in polynomial time. So the central question is which of those CSPs can be solved in polynomial time, can be solved efficiently, and for this we have to understand when can they be solved in polynomial time. And if you want to understand this, you also want to understand when you don't expect to have such an algorithm. So we want to understand when these problems are NP hard. We have this famous conjecture, Federawardi dichotomy conjecture, which says finite domain CSPs are either NP or NP complete. And this has been solved has been announced actually for the first time, even before it was announced at the conference's stock, at an AAA in Novi Sad in 2017. The solution by Andrei Bulatov and Dima Shuk, which got them, the problem got this Alonso Church Award. And the central ingredient is the universal algebraic approach. I mentioned this already last time. We can use this Galois connection between invariant relations and polymorphisms that I have explained last time to see that the complexity of the constraint satisfaction problem is fully captured by the polymorphisms of the structure B we started with. All right, I will be quick here. I will immediately jump to infinite domain CSPs. A very good running example here is maybe the CSP, we'll see it later again, for the rational numbers with the weak linear order and the disequality constraint. This can be solved in polynomial time. Another example of a CSP, which is NP hard, is the CSP for the betweenness relation. Has the same domain, but this time we fix a ternary relation, which contains all those triples where x is smaller y or smaller z, or z is smaller y, smaller x, so y should take the middle value. This is a famous example of an NP complete problem. And I'm saying this is a first order reduct of the structure Q with the strict order. What does it mean? A first order reduct is a structure with the same domain, so that all relations are first order definable over the structure we started with. So the first order definition here, you are allowed in particular disjunction. And the nice thing about first order reducts is that the respective polymorphism clones will again be oligomorphic. Why? Well, we have potentially more automorphisms. This is, we have potentially only less invariant relations. So in particular, we have finitely many, so they will be oligomorphic. The universal algebraic approach can be applied. This is what we have seen last. So we can use polymorphisms to study the complexity. And in particular, the universal algebraic approach works if we start with a structure which is homogeneous with a finite relational signature. Also, I said finitely homogeneous. All right. So let me jump right into some bad news. Even though we put these strong model theoretic restrictions, even though we might only be interested in oligomorphic clones, we have some negative results about the computational complexity of the constraint satisfaction problem. And this comes from the fact, due to Hansen, we use an old construction of Hansen. Hansen constructed 2 to the omega many homogeneous directed graphs on a countable set. And one can prove that they all have pairwise distinct CSPs. So we only have countably many Turing machines. There must exist CSPs of this type that are undecidable. So it seems that if you want to really hope for some systematic understanding, we have to throw in another assumption. Oligomorphicity alone is not enough. And the assumption in the context of CSPs, which is still very general, but makes things much nicer, is what we call finite boundedness. So let me describe this. So we have a structure. Already last time I defined the age of the structure. This is the class of all structures with the same signature that are finite and embed into the structure we started with, into B. That's the age of B. Now, the age sometimes can be described combinatorially with a finite amount of data in the following way. We fix a finite set of finite tau structures, n for no structures. We forbid them. So we look at the class of all finite structures that do not embed any of these no structures. So this will be denoted by fork of n. And I call a structure B finitely bounded if there is such a finite set of finite forbidden structures that describes the age. So age of my structure should be precisely the set of this class form of n. An example, my running example, if we start with the linear order, well, we certainly don't have directed cycles, and in particular, no directed 3-cycle. We don't have back and forth edges in Q. We don't have loops. And you should not forget, we also don't have pairs of elements that are incomparable. But since we forbid structures induced, we forbid embeddings, this will also be so it's important. We can forbid 2 points that are not related by edges, by this way. And then it's possible to get all finite structures. All finite structures are finitely bounded. So this generalizing the finite setting. Okay, and now we can, in this setting, we not only we are again back in the world where we hope to get a complete understanding. There is a conjecture with Michael Pinsker that we actually, I think we announced it for the in Toronto, I think, at the CSP workshop in this form. So I fix a structure which is either finitely bounded, either finitely bounded or a first order reduct of a finitely bounded structure. This makes the class more robust and even bigger. And then the CSP is either NP hard or NP. NP hard, in fact, NP complete even, because for reducts of finitely bounded homogeneous structures, we're always in NP. It's good news. So NP, I could even write here NP complete. So, and this has been confirmed. For that we had already, the finite case is a special case, but it has also been confirmed for first order reducts of the rationals, the order, first order reducts of the random graph, first order reducts of various fundamental omega categorical homogeneous structures. Also for all CSPs that are expressible in the logic MMSNP, for monotone monadic SNP, which was one of the motivations of Federavardi to introduce their conjecture. So MMSNP can also express some infinite domain CSPs. All of them are omega categorical. All of them can be formulated with an omega categorical structure B. And in fact, actually, I'm slightly lying here. In fact, this has already been proved here, that the dichotomy has already proved by Federavardi and Kuhn. And the contribution that Antoine Mottet and Madeleine and myself that we brought here is that we will verify an algebraic dichotomy conjecture even here. So okay, I will continue. So what's the most powerful hardness tool that we have in the area for proving hardness of omega categorical CSPs? It's PP constructions, as in the talk of Jakub Opperschall that we just in the tutorial that we just heard. So what is a PP construction? Something more flexible, something more powerful than PP definitions, and even more powerful than PP interpretations that we have seen last time. It's you first take a PP power. So you start with some structure, you look at the set of all D tuples, and then you define on these D tuples some relations. So if your relation that you want to define has arity K, you can, the condition is that the resulting D times K array relation is primitive positive definable in the structure B you started with. So a PP power should have this property. All of its relations are definable already over the base structure B with primitive positive formulas. That's the first step. That's a PP power. And then in the next step, we allow homomorphic equivalence. So a structure is PP constructible if there's a PP power which is homomorphically equivalent to it, which has homomorphisms in both ways. All right, an example, C9, so the directed cycle with of length 9 is, for instance, PP constructible over a cycle of length 3. You take the third power, you will get 3 to the 3, so 27 vertices. You can verify that the relation that I wrote down here, so you see it has 6 variables. So over triples, it will define a binary relation. So the resulting graph defined by this formula will have 3 9 cycles, if you do the computation. So it will be homomorphically equivalent to C9. So C9 is PP constructible from C3. C3, this one. All right. So if you want to understand PP constructibility, it's very complicated in general on finite structures. But if you're interested in only when do directed cycles or unions of directed cycles PP construct each other, we have a complete picture. This is some joint work with Florian Starke and Albert Bucay. It's just very recent. All right, what's the motivation for the CSP that we have already seen? Even in the promised CSP, this is the right. This appeared in the Wonderland of Reflections paper, which is, and it's really a wonderful tool. Yeah? It's a wonderful title because it's really a wonderful tool. PP constructions are fantastically flexible, and as we will see in a second, they have not only over finite domains, also over infinite domains, they have a very nice algebraic characterization. So I will algebraize my hardness condition. So yeah, we have seen already previously if K3, which has an NP complete CSP, is PP constructible in my structure, finite or infinite, doesn't matter. If it's PP constructible, it's CSP. That's here, there's a typo. This should be CSP of B. Then CSP of B is NP hard as well. And this is precisely the condition for hardness for finite domains verified by Bulatov and Juk. Okay, well, what's the algebraic version of? We have already seen this concept in the talk of Jakub Opperschall, but he used a different name. So there are actually various names in the literature. So there's H1 homomorphism. Then there is minion homomorphism. And I also like a minor preserving map, because that's actually what they do. These are maps between clones or between sets of functions, but here in this talk, only clones, function clones. So maps that map the operations of one clone to the operations of the other clone, so that minor taking is preserved. You know? Composition with projections, basically, is preserved. And now something new, of course, because this didn't play a role in the finite. Here, some topology will be important too. And if you want to generalize this to the infinite, I say a function between two function clones, maps operations to operations, is uniformly continuous if for every finite set of my domain is countable, say, natural numbers. For every finite set F of the domain, there is another finite set. Imagine it as a larger, maybe finite set. So that for every arity n, for every function f and g in the first clone of arity n, if these functions agree on g, they also agree on f. No? That's uniform continuity. And now, in the wonderful Wonderland paper, there is a proof that K3 has a PP construction in a structure which is finite, or, it is already in the Wonderland paper, omega categorical, if and only if there's a uniformly continuous minor preserving map from the polymorphisms of our structure to the polymorphisms of K3. Well, the polymorphisms of K3, we know they are essentially unary, they are essentially permutations. So it's a trivial, that's the trivial clone. Yeah. All right. The uniform continuity can't be dropped. Yeah, that's another recent result. All right. So now with this tool, one can attempt to formulate a conjecture, which infinite domain CSPs, well, with the assumptions I made, yeah, first order reduct of finitely bounded homogeneous, which of them are hard? Well, we have seen a tool already, and which of them are hopefully in P, all the others, hopefully. Yeah? So let me look at this. Yeah? So we have a structure, which is a first order reduct of a finitely bounded homogeneous structure, and I'm assuming it's a model complete core. Because this will, well, certain items will work without this assumption, but I want to state many equivalent items. And so I would like to make this assumption. This assumption was mentioned in my previous tutorial at the very end. It's a very natural assumption. We can make it without loss of generality in some sense. So we have a structure which is a model complete core also. Then the following are equivalent. 1, our strongest tool to prove NP hardness from the previous slide. 2, something that you might have seen already for finite structures. So in the finite, the traditional way of presenting the dichotomy is that you, at the very beginning, you say we have a core. Second step is we can reduce to the idempotent case. And once we have the idempotent case, we can work with clone homomorphisms. And this actually is also feasible here. So we say, well, we already know we have a model complete core. So we are hard if, I mean the negation here. Yeah. So here 1 says our strongest tool fails. 2 says if whenever I fix finitely many constants, and I stabilize my clone at these constants. I require that I'm only looking at polymorphisms that fix those constants too. Then the resulting clone should not only have a minor preserving map to the polymorphism clone of K3, but even a clone homomorphism. Even a map that fully respects composition. Yeah. All right, so this is 2. And this is how we originally phrased it already in 2011 with Michael Pinsker. We already by then said, well, this is a very strong tool for proving hardness. Everything else should be in P. And it turns out that 1 and 2 are equivalent. Third item, this is what I would have liked to talk about last time already. The polymorphisms of B. Well, from the finite, we know Siggers polymorphisms. We have seen them in Jakub Opperschall's talk. But here we have an almost version of Siggers polymorphism. So Siggers polymorphisms are, let's put them like this: x of x, y, z. Well, we had them. It takes me too long to draw them. Huh? So we had them on the previous slides of Jakub Opperschall in the tutorial. But the change now is that we allow also to first apply an endomorphism and a unary polymorphism, and then comes only the Siggers identity. So modulo applying unary maps in the polymorphism clone, we have a Siggers term. All right. So yeah, so the equivalence between 2 and 3 is from the paper of Libor and Michael. Here it's important that we have this assumption of model complete core. The question whether the negation of 1 implies, whether 1 implies polynomial is sort of also in the Wonderland paper, and it's a stronger hardness condition. So this was also, and then there was a paper where these many authors proved that the conjecture 1 and 2 are equivalent if you are a first order reduct of a finitely bounded homogeneous structure. So that's where we need the other assumption in my theorem. So you see we have many equivalent items, and yeah, the big question is now, do these equivalent items, if they apply, imply that we can solve the CSP in polynomial time? And this is open. All right. But it's true in many special cases. In all of these cases that we have seen earlier here, in these partial classifications, in all of these partial classifications, it turns out that the border between easy and hard problems are precisely as described in this graph. All right, so let me continue. So in this tutorial, I will omit some important topics. One important topic that I will omit is the usage of Ramsey theory to hopefully, to get partial results, or hopefully eventually to prove the conjecture. So Antoine Mottet has several important results in this area, but also Bertalan Bodo has some quite strong results when how to use Ramsey theory to make progress on the conjecture. And we have the talk of Michael Pinsker. Yeah, that is right after this tutorial, and I'm very much looking forward to this because it will bring some new results, more advanced. All right, what I want to do in the rest of the tutorial is to mention some applications. Yeah, to illustrate oligomorphicity is not rare. So at the first sight, you might think this has nothing to do with universal algebra, but then oligomorphic clones come in the picture. In finite model theory, there are some very important logics that very much at the center of the interest is monadic second order logic and data log. In monadic second order logic, you can quantify, so it's an extension of first order logic, where you can also quantify universally and existentially over unary predicates. I have drawn you here a little example of such an MSO sentence. And basically, if you read this out, well, it has a single binary relation E, so it's a property, talks about properties of graphs. So if you have a finite graph, so when does it satisfy this sentence? There should exist a subset of the vertices, which is not empty. Yeah, so I'm drawing it, subset of the vertices. Okay, here it is, that's my ZX. So that every element in this set has a successor. Yeah, so we have some edges, and it should go on like this. Well, and if you're in a finite graph, you eventually must run into a cycle. So you can check that this sentence is true if and only if your finite graph has a directed cycle. So you see, MSO is a convenient tool to specify properties of finite structures. And that's how finite model theorists use MSO. It has some nice properties. For instance, MSO sentences can be evaluated in polynomial time if on classes of bounded tree width. Another important logic is data log. Data log is somehow like prolog without function symbols. It's like little programs that consist of rules. So again, let's look at an example here. I have drawn you an example. Again, my only input symbol, which only appears on the left, is this symbol E. So again, we are talking about the property of graphs. Let's draw a little graph. Maybe this one. So how does data log work? Data log takes this graph and applies the rules whenever it can. For example, we have the first rule, E implies T. So if I have an edge in my graph, I can add a T edge. I can. Then I also have the second rule, which establishes somehow transitive, that T is the transitive closure of E. So I can derive these edges, all of them, and eventually even a loop. And then I have the third rule, which says, oh, if I see a loop, I derive false. So the idea here is, again, that this data log program accepts precisely or derives false for precisely those finite structures that have a directed cycle. So these two things, describe the same property in very, very different ways. And both of them have their advantage. The big advantage of data log is that data log programs can always be evaluated in polynomial time. And there are some logics that are contained both in MSO and in data log. And this is great because somehow you can then combine the positive features of both logics. And also sometimes you gain some extra conditions. For instance, if a property is expressible both in MSO and in data log, then containment between properties becomes decidable. Containment between data log programs is undecidable, containment between MSO sentences is undecidable, but if you have both, things become very nice. Yeah? So we would like to understand which properties are both in MSO and in data log. And this is where oligomorphic clones and universal algebra comes in. It's very surprising because there's no, it's not visible that this should have anything to do with oligomorphicity or even universal algebra. But it's true. So we have the following recent result with Simon Kneuer and Sebastian Rudolph. If you have a class of finite structures which is both in MSO and in data log, it is a finite union of CSPs of omega categorical structures. So in particular, if you start with a class of structures which is sort of the yes instances of a constraint satisfaction problem, few yes structures, which can be expressed in MSO, one can prove that this is a part of the proof. Actually, we prove also this. Then it's the CSP of an omega categorical structure. Yeah. So you can use oligomorphic clones to study these classes and all the universal algebra that is involved. And you might then also attack questions that are of interest in database theory and in finite model theory. For instance, is your data log program maybe also a symmetric data log program? Is a given MSO sentence maybe expressible in symmetric data log, which is a fragment of data log? All right, so this is one application I wanted to mention where CSPs are not part of the problem description, rather part of the solution, hopefully. Yeah. Another application is relation algebra. So this is a part of universal algebra, but I should still warn you that you should not confuse relation algebras with relational algebra. Relational algebra is a term that is used in database theory. It's another way of saying first order logic for them. Huh? So this is not the same. It's also not the same as a relational clone when studying Galois connections. A relation algebra is something very different. It goes back to Tarski and has been studied by many people since, and it's a nice area. So we have an algebra which has the signature of Boolean algebras. And additionally, we have a binary operation for composition, a unary for a constant it, and a binary operation for taking inverses. So what's the idea? The idea is that the elements of this algebra stand for binary relations. So we can take unions, intersections of them, we can take complements, but we can also compose binary relations. And we can take inverses of inverse relations by flipping the arguments. And we have we have equality as a special relation. And you can now do universal algebra with those. And so what people in relation algebra are interested in is the so-called network satisfaction problem. It's one of the basic computational problems in the context of relation algebras. So here you study networks. I have drawn you here on the right, I have drawn you such a network. And networks, they have a finite set of variables. And between any two variables, you have to specify an element from your relation algebra. If my relation algebra is, for instance, the relations over Q, strict order, less than, greater than, and so on, this equals all q squared. Well, the composition table between the basic relations I've drawn you here. Then this would be such a network where I can label, for instance, that two variables should be in the relation less than or equals to. And the question is, given such a network, is it satisfiable in some representation of the relation algebra? For instance, in Q. Q, you can check, is a representation of this table that I've drawn to you. And the question already goes back. This is older than CSP. It's older than the Federavardi paper. It's already in '95. Hirsch asked, for which finite relation algebras A can we solve the network satisfaction problem for A in polynomial time? Yeah, and we have to be careful. Yeah, it looks like, oh, it's a finite template here, but it's not true. It's the representations. Your relation algebra is finite, but the representations might have to be infinite. And so this problem can even be undecidable. Yeah, we have to be careful. But there is a link, again, to CSPs, and even better, there's a link to oligomorphic clones in this context. And the link is strongest if you have the extra assumption that your relation algebra has a normal representation. This is something that has introduced by Hirsch also. Most of the natural examples that are used in relation algebras do have such a normal representation. And then the network satisfaction problem for A is equivalent to the CSP for an infinite structure. That's already nice. And it's even a finitely bounded homogeneous structure. And it's even a model complete core. So all the nice properties that I have discussed today, all of them apply. So we are really fully in the framework of our dichotomy conjecture. And some things that can then be proven is that if your finite relation algebra has some extra assumptions, for instance, if it's one of these extra assumptions is that all relations should be symmetric. And the other one is that it has a flexible atom. I will not define what this is, but it's a property that they study in relation algebra. Then you always have such a normal representation, and the infinite domain tractability conjecture holds. Now, the three conditions that I've listed on a previous slide, they imply tractability. All right, so this is another surprising link and application of oligomorphic clones. And I would now like to jump back to my first talk, where I didn't manage to discuss everything. In particular, I didn't manage everything that I needed for my homework assignment. Yeah, you all worked hard yesterday night on my homework assignment, and so I want to go back into this. So last time I introduced model complete cores. Let's just quickly recap what they are. They are those structures where the automorphisms are dense in the unary polymorphisms. So the closure of the automorphisms are the endomorphisms. We have seen examples. We have seen that they preserve height 1 identities. Identities, they transfer to the model complete core. Oh no, this we haven't seen. Sorry. We have seen that height 1 identities in model complete cores are stable under adding constants. That's what we have seen. What we have not seen is what happens if a structure is not model complete core. Then we can always find, if we start with an omega categorical structure, we can always find another structure which is homomorphically equivalent and is a model complete core. And this model complete core structure will even be unique up to isomorphism. And it will again be omega categorical. And this homomorphic equivalence, meaning having homomorphisms in both directions, will preserve height 1 identities. Some very easy facts that you can verify. So it goes together with these minor preserving map concepts. And to just give you an example, so I claim the Rado graph, which is the up to isomorphism unique homogeneous graph that contains all finite graphs as induced subgraphs. This wonderful graph, it's not a model complete core. because it contains infinite cliques. But one can prove that it's easy to prove that it's homomorphically equivalent to an infinite clique, and the infinite clique is a model complete core. So we say the infinite clique is the model complete core of the Rado graph. All right. All right. So, and this is now the operation that I've mentioned today. I wanted to mention it already last time. This is the result. If you have, yeah, this is the result from the finite. Let's not look at this. If you have an omega categorical model complete core, then we have this equivalence. Yeah, I talked about this equivalence already today. And now I come to the exercises. The exercises are about the Johnson graph. The Johnson graph is the line graph of the infinite clique. So what is the line graph? If I have a graph, for instance, K5, the line graph will have as vertices all the edges. Yeah, so the edges become vertices. And two edges are adjacent in the line graph if they share a vertex. Then I make them adjacent. So if this is this edge and this is this edge, then they would be adjacent because they share this vertex. Yeah. All right. So for instance, for the K5, the line graph is the complement of the Petersen graph, it turns out. So my first question is a pol of the line of this Johnson graph, is it oligomorphic? This is something that you could have already answered with the stuff that I didn't skip last time. So any opinions on this? Now, how does this work? Michael, you have to, oh, I see this. Is there also the option to do this? Because if not, then Michael, you have to help me moderate now. Michael or Michael.
Yeah, unfortunately, I cannot accept raised hands. I also don't see them.
But you see, if this is the only thing that you can do, this is not fair because the answer might be yes or no. Huh?
So,
most people
write their answers in the Q&A feed.
In the Q&A. I can't see the Q&A. Yeah?
Well, I confirm we have no answers.
No answers. On Slack, one could look at Slack. No. Anyway, that was one question. And I interpret now this as, yes, it's oligomorphic. What's the reason? Well, oligomorphicity is about counting orbits. And now it turns out the line graph, you can interpret it over the clique, you know, by a binary interpretation. So you can easily transfer bounds to structures that are interpreted. So you can easily bound the number of orbits on n tuples in the Johnson graph. Basically, the automorphism group of the Johnson graph is just a different action of the full symmetric group that acts on the infinite clique. Now it's basically a different action of the infinite symmetric group. It's another way of seeing it, maybe. All right. So that's one answer. But now the question is, what is the model complete core of the Johnson graph? So I guess, first of all, it's not a model. It's apparently not a model complete core, by the way I phrase it. Why not? Yeah. And what is the model complete core? So I see on Slack, no one's answering on Slack. No. So this is strange that you no, is there? Raise hands. Q&A. Now I click here. Q&A. No.
Yes, well, I'm taking care of Q&A and raise hands, and I don't see anything.
Okay, no one solved my exercise. This is a pity.
Slide.
Sorry? Okay, so the answer here is, what's the model complete core of J? Well, J has infinite cliques. So it will homomorphically map to an infinite clique, which then homomorphically maps back to J. So the model complete core of J is an infinite clique. And now you can work out the other exercises as well with this. And the remainder of the slide. I mean, you need basically lots of things that I mentioned en passant on the slides, and with these things you can solve this exercise. All right, it's 46. Yeah, thank you very much for your attention, and I take questions.